Welcome to True Projects. In this video, we are going to see a novel wireless network intrusion detection method based on adaptive synthetic sampling and an improved convolutional neural network. Introduction. The increasing cyber threats in the modern network landscape demands effective intrusion detection algorithms. Current solutions have limitations due to evolving tactics by malicious actors. This project addresses the issue of imbalanced data distributions, which contributes to skewed detection rates. By mitigating data imbalance, novel approaches aim to enhance intrusion detection mechanisms' robustness. Objective of the project. The project aims to develop an innovative wireless network intrusion detection approach addressing imbalanced data distributions and enhancing detection accuracy. It utilizes adaptive synthetic sampling (ADASYN) and an enhanced convolutional neural network (CNN) with feature optimization (SPC-CNN). The proposed SPC-CNN will be benchmarked against NIE-based and SVM using the NSL-KDD dataset, aiming to provide an efficient and accurate intrusion detection solution. Requirements. These are the requirements needed to execute this project. Hardware requirements: operating system of Windows, processor of i5 and above, RAM of 4GB and above, hard disk of 20GB and above. Software requirements needed are Python, ideally of Python 3.7 version. To execute this project, we have designed the following modules. The first module is Upload NSL-KDD dataset. In this module, the NSL-KDD dataset, which contains both numeric and non-numeric data related to network traffic and attacks, is uploaded. The dataset comprises various attack categories like denial of service, DOS, remote to local, R2L, user to root, U2R, and probe. This dataset serves as the foundation for evaluating the performance of intrusion detection algorithms. The second module is preprocessed dataset. The preprocessing module transforms the raw dataset into a format suitable for algorithmic processing. Non-numeric data is encoded into numeric values, enabling algorithms to work with the dataset effectively. Further steps involve data normalization, handling missing values, and shuffling the dataset to ensure optimal performance during training and testing. The third module is ADASYN augmentation. This module utilizes the adaptive synthetic sampling (ADASYN) technique to counteract class imbalance within the dataset. ADASYN generates synthetic instances for underrepresented attack classes and ensuring that all classes have an approximately equal number of instances. This data augmentation aims to improve the algorithm's ability to classify rare attack types. The next module is dataset train and test split. The dataset is divided into training and testing subsets. Typically, around 80% of the dataset is used for training the algorithms, while the remaining 20% is set aside for testing the algorithm's predictive performance on unseen data. This module ensures a fair assessment of how well the algorithms generalize to new data. The next module is Train SPC-CNN algorithm. The SPC-CNN selective pruning and clustering based convolutional neural network algorithm is trained using the augmented dataset. Unlike traditional CNNs, the SPC-CNN focuses on optimized feature extraction by removing irrelevant or redundant features. This approach enhances the algorithm's ability to capture essential patterns in the data, potentially leading to higher accuracy in intrusion detection. The next module is Run NIE-based algorithm. The NIE-based algorithm, a probabilistic classifier, is trained and evaluated using the preprocessed and augmented dataset. NIE-based assumes that features are conditionally independent, simplifying the classification process. Its performance is compared against other algorithms to assess its suitability for intrusion detection. The next module is Run SVM algorithm. The support vector machine SVM algorithm, known for its ability to handle complex data distributions, is trained and tested using the prepared dataset. SVM aims to find a hyperplane that best separates different classes. Its performance is evaluated alongside other algorithms, indicating its effectiveness in detecting network intrusions. The next module is Comparison Graph. This module generates a comparison graph that visually displays the performance metrics of various algorithms. Accuracy, precision, recall, and F-score, among others, are plotted for each algorithm. The graph provides an intuitive way to compare the strengths and weaknesses of different algorithms in the context of intrusion detection. The last module is predict attack from test data. In this module, the train SPC CNN algorithm is applied to predict the attack category for a given set of test data. The algorithm analyzes the features of the test instances and assigns them to one of the predefined attack categories. This module showcases the practical application of the developed solution in real-world scenarios. Execution of the project. To execute this project, first we need to open the code folder. This is the dataset folder in which I have KDD dataset and test data. I am opening the KDD dataset. So these are the column names and the remaining rows represents dataset values, and in last column we have attack class labels called DOS, R2L, U2R and probe. So by using this dataset we will train and test performance of all algorithms. Close this dataset, and this is the test data. So in this data I don't have the label column. We will predict it using the trained algorithms. Close this, and this is the model folder in which I have pickle and .hdf5 files which contain algorithm information. These files can be loaded into the project code during runtime to utilize trained models. This is the Python main code file, and this is the table HTML file which will be loaded into the application later, through which we will display the performance metrics of all the algorithms in a tabular format in the web. This is the run.bat file. Instead of executing the project in command line interface, we have created this Windows batch file. Double click on run.bat file. This graphical user interface will be opened. With this, we are interacting with the program. We have used Intrusion library to create this graphical user interface. Now click on Upload NSL KDD dataset button. A dialog box opens. Select the dataset and click on Open. So in this graph, on x-axis I have the attack names, and on y-axis I have the count of records. And we can see one attack has so many records and other attack is having very few records. This issue is called as class imbalance. Close this graph, and in the text area we can see a confirmation that dataset is loaded, and these are top 5 rows of the data and these are bottom 5 rows. There are 11,578 rows with 42 columns in the data. And we can see there are non-numeric as well as numeric values in the data. Now click on Preprocess Dataset button. So we have pre-processed the dataset, that means all non-numeric values are converted to numeric now, and we have normalized the data and shuffle process. And now click on Adjacent Augmentation button. So after augmentation, all class labels are having equal number of instances now. Close this graph, and here we can see the count of each attack. Now click on Dataset Train and Test Split button. So total number of records found in dataset are 23,972, and this total records are further split into train and test sets in the ratio of 80:20. Now train set includes 19,177 records and test set includes 4,795 records. Now train set is used to train the model and test set is for evaluating the performance of the model. Now click on Train SPC CNN algorithm button. So this is the Adjacent SPC CNN confusion matrix. In this graph, on x-axis I have predicted class and on y-axis I have true class, and the diagonal boxes, the yellow color boxes, are the correct predictions and the remaining boxes are misclassifications, and we can see there are very few misclassifications. Close this graph, and here we can see the performance metrics of Adjacent SPC CNN model. Now click on Run Naive algorithm button. So we can see there are many misclassifications here. Close this graph, and here we can see the accuracy, precision, recall and F-score of Naive algorithm. Now click on Run SVM algorithm button. So in this graph, the diagonal boxes are the correct classifications and these are all misclassifications, and we can see there are many misclassifications. Close this graph, and here we can see the performance metrics of SVM algorithm. Now click on Comparison Graph button. So here we are displaying the comparison metrics, the performance metrics of all the algorithms in the tabular format in the web. Close this, and in this graph on x-axis I have the algorithm names, and on y-axis I have performance metrics, accuracy, f-score, precision and recall. And we can see SPC CNN model is doing well when compared to naive-Bayes and SVM algorithms in this particular project. Close this graph and now click on Predict Attack from Test Data button. A dialog box opens. Select the test data and click on Open. So here we can see in the square brackets I have the test records, and after square brackets we can see the attack predictions. So for this test record it has predicted the attack as probe, and for this test record it has predicted the attack as R2L. Similarly, we can scroll down test area to see the predictions for all the test records. The conclusion here is this project introduces a novel approach to network intrusion detection using adaptive synthetic sampling and optimized SPC CNN algorithm. This enhances data balance, improves accuracy and reduces false alarms. Comparative evaluation against naive-Bayes and SVM highlights its significance. This work contributes to advancing intrusion detection capabilities and paving the way for more robust and effective network security solutions.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.